Okay, good afternoon everyone. My name is Tiago Domingues. I'll be presenting this work. There are other authors who work on this project. Their names are over there, Pedro, and Pedro Moreira. I am from Inenzi. My presentation will consist of mainly 4 parts: an introduction in which I'll explain some of the setups that you have to do this testing. Then I'll discuss some of the tensile testing that I've done and the results. The same for the fatigue testing, and finally some conclusions and some remarks regarding the future works. As a motivation for this work, I believe that we have higher interest in additive manufactured parts, especially parts that can be formed structurally well, and thus the study of plastics with better performance, in this case high performance plastics, so we can find out the max that we can extract from this kind of parts. So that's what we did. We tried to study fatigue and tensile properties of these additively manufactured parts, in particular for PEI material. So just to give a bit of an insight, high performance plastics are plastics that are printed at higher temperature and usually have better mechanical, chemical resistance and also better resistance to temperature. In this particular case, we are studying this PEI material, which you can see is printed at a very higher temperature than the usual plastic printing materials, but also has better mechanical properties compared to the other ones. More specifically, we use this material from 3D form makers, just showing you in case you want to repeat the experiment and are expecting the same results. I assume that if you change the material, the results might change a little bit also. Similarly, I'm presenting the printer that you use, as I believe it has an impact on the results shown. In this case, we have kind of a homemade setup that we adapted from an existing printer, which is a CubeX 3D printer, to which we added a E3D extruder and heated bed specifically for high temperature plastics. We also developed air environment heating system, in which you have a heat gun to kind of push the temperature in the air up to 100, and then you have a radiation system that we estimate will increase the surface temperature by 30 degrees. And finally, we also have cooling for the motors and the new control motor, but that shouldn't affect as much the producing of parts. For tensile testing, we follow this standard. You use type 5 specimens, which are small specimens, which might diminish a bit the results, but we had to be conscious in terms of the material. The speed rate that you use is 1 millimeter per minute, and we did this testing on an instrument machine and used the IC for doing the strain measurements. As for the tensile testing, we printed with extruded temperature in 4 levels in order to try and identify if the optimal parameter for printing, and we did at 360, 70, 80 and 90. And then the rest we kept all the same, which was 200 for the heated bed, the ambient temperature at 100 plus the radiation system. We set maximums for printing speed and acceleration at 30 millimeters per second and acceleration of 100 millimeters per second square. The properties of printing that we chose were kind of standard that we believe would maximize the results. So in this case, 100% in field with plus 45 and minus 45 orientation of the infield, and we had 3 parameters for each layer. The results shown are the following. So these are the strain stress curves for the 360, 370, 380 and 390 degrees of printing. We didn't find any major difference, and we also find that the properties vary a lot even within the same range, which leads us to conclude that probably there are other factors influencing these specimens more than the temperature. We tried to even assess the fracture surfaces in order to find some clues on why this was happening, and we also couldn't find any major reasons from these images that would show us in this way. This is again the surface fractures for 360, 370, 380 and 390. These are examples for each of the temperatures. So in comparison, to try and make some sense of these tensile results, so we have a little bit of this dispersion here, but in general we can say that we have a max stress of around 90, 85, which is a little bit below the manufacturer specification, which we believe to be in accordance to what was expected. And we also have a big variance in ultimate strain. But you can see here that the major finding that we find is the slight increase in temperature kind of produces a slight increase in ultimate stress, and it produces a more stable ultimate strain. So in this case, you have here these error bars that are decreasing, especially in terms of strain when the temperature goes up. So we believe this to be a good result. In terms of fatigue testing, we use this standard in which you use the exact same specimens as the standard states. The frequency that you use for testing is 10 Hz. The only concern is the heating of the specimens, but from the first testing we control this using a thermographic camera, and we were able to tell that there was no particular heating that we believe would affect the performance of the test. We used the same machine, and in this case we did tests with a stress ratio of 0.1. For this fatigue testing, the printing parameters chosen were 370, which is kind of in the middle of the range specified by the manufacturer of the material, so we believe to be the most common printing parameter. And then we kept all the rest as just for the tensile testing. In terms of the results, we had, I must say, we had a lot of bad results in which the specimens broke outside the limit, which I believe it's a pain. Everyone that tries to do this kind of study with polymeric materials will find. But for the ones that is okay, this is how the results shown, which use the Fatigue Pro software to produce this SN curve, which we believe to be a satisfactory result. As for the fracture surfaces, we did again the analysis and found some kind of interesting results. So these are examples of specimens that break at 25% of the ultimate strain as a max stress. This one's for 20% of ultimate stress, and this one's at 50. In these ones you can see that the cactus was a bit smoother as it has this more shiny surface and then the more violent burst. In this we can have an intermediate situation, and finally the last one didn't have any kind of smooth growth. It was a more abrupt breaking. So in terms of conclusions, we can say that we were able to do tensile and fatigue testing in PEI for the 3D printed specimens. A comparison between the ultimate stress and strain were made for the specimens at the 4 temperatures, and some conclusions were found, such as there is an increase in ultimate stress for higher temperatures, and the ultimate strain becomes more stable at higher printing temperature as well. And we were able to produce an SN curve for 3D printed specimens with our fatigue testing. In terms of future works, we believe that we need to be more extensive in the study of parameters that affect the mechanical behavior of our specimens, as clearly temperature is not the only factor, or even probably not the most important factor in this case. And we also found that we need to improve a bit our printing capabilities, because as you can see in the photos from the breaking surfaces, our geometry is not perfect, and this might also influence the results that we're having. So we really need also to improve on this. And this will be all from my side. If you have any questions, feel free to do so.
So we have a lot of time for questions, if you have any. More questions? One from my side. Are you going to test also in thermal fatigue at high temperature?
I'm not considering that yet, but for sure it's a case, yes.
What do you believe can expect it from the test?
For sure it will worse, where I have no major experience in that kind of testing, so we were kind of running away from the thermal fatigue testing And also I believe we have some issues to resolve in terms of finding the other properties within the specimen that we need to solve before going to that kind of more advanced testing, I believe.
Yeah, okay. Did you also find by microscopic analysis of the fractal surfaces the origin of the crack under fatigue? Or
in most cases, the origin of the crack is in the surface that is placed on the heating bed, which we believe is caused by the temperature gradient. In some cases, you find that it's not from that place, and usually we believe it's because it has some kind of predetermined defect in the specimen. Actually, I think you can see an example here. So most of them are from here and from here, which is exactly the place where the surface where the specimen was printed. And in cases like this one, this is, for example, a case in which you had lower cycles than usual, and it came from the side, so we believe this had like some kind of defect originating the crack. But in most cases, it's from the surfaces in which it was printed.
And did you prepare the samples before testing, polishing?
No, we did no sampling.
Just
as printed.
Okay. So thank you again. From the audience.
Yes. Could you explain a little bit about the material that you tested? Is this a thermoplastic or thermoset?
No, it's a thermoplastic.
Thermoplastic?
Yeah.
Okay, if you go to your fatigue curves, can you show your fatigue curves?
Yeah.
So what kind of test frequency did you use at different levels?
10 Hz.
At all the levels?
Yes.
Well, it is well known that frequency significantly affects fatigue performance. So using the same frequency at high load level versus at low load level, I don't know, how distorted the results will be. It is a well-known fact. I mean, thermoplastics, it's very frequency dependent when you do fatigue tests.
So you suggest that I do?
You have to take frequency into account in thermoplastics. Yes, it's in some cases actually higher frequency increases fatigue life. In some other cases it decreases fatigue life because of the temperature it produces.
Okay.
So frequency is an important factor. It's not like metals where you, regardless of what frequency you test, assuming you don't have much plastic deformation, that the results are not very sensitive. But in thermoplastics, they are.
The only thing I did, considering that fatigue, the frequency problem, is monitoring the temperature during the testing, using a thermographic camera to make sure that I have no variation in temperature, so I would have no thermic effects affecting the fatigue life of my
Well,
specimen.
with regards to temperature, first of all, you're only looking at the surface temperature, not the internal, right? So you don't know how much internal heating is going on.
Okay.
But it's not just the temperature. The strain rate effect has a very significant effect on fatigue of thermoplastics.
Okay, I will make sure to consider that in the future. Thank you.
So, any other questions? Okay. Thank you again.
Thank you.